Hi there, this is Mr. Deiulis, and this is going to be my first real content-specific video for AP Physics 1. So let's get right into it, but keep in mind that I will not be going over the conceptual aspect of these things, only the mathematical aspect of it, because I want you to be able to kind of hit the ground running in terms of solving problems. But in terms of having a deeper meaning, you're going to have to wait till we're actually in class a little bit, because it's easier for me to do that in class, doing some demos, doing some activities with you guys. But the math, at least, I can get across to you now. So just keep that in mind, that there will be a greater meaning to you later. Okay, I'm not going to leave you guys hanging on this for too long. So first things first, the triangle symbol, it is delta. It means change. So anytime you see it, it will mean change. Next we have position. Position is represented by the letter X. Position is where you are at any particular time. And so X without any subscript means that that's where you are at that time. That is your final, typically. Sometimes in some textbooks you will see an F. That's really supposed to be an F for final position. And it simply just means it is your position where you end up at that time. Displacement. Displacement is the change in position. So it's where you are now compared to where you used to be. So x minus x naught, or x sub 0. It's easier for me to say x naught. So that means x at time 0. That is x at time 0. That should make some sense. So it's the position where you are now minus the position where you were when somebody clicked the stopwatch when it was reached, when it had a time of 0 on it. And that is also known as delta x, the change in displacement. The change in position, your displacement. Velocity. So velocity is going to be the change in position, otherwise known as displacement. So let me just write it the long way first. So x minus x naught divided by time, so t minus t naught, otherwise written a bit more simply as delta x over delta t. In fact, usually the delta isn't even really expressed with the t in a lot of cases. You typically do want to keep it with the x at least. It is assumed that time is changing because, well, that's what it always seems to do, doesn't it? Acceleration is, for you calculus people, or at least maybe going into calculus this year, you'll hear the word. It's the derivative of velocity. Don't worry, you don't need to know that too much. It's just a buzzword, if you will. So acceleration is going to be the velocity minus its original velocity over the same thing in terms of time, t minus t naught, otherwise known as the change in velocity over the change in time. So if velocity is changing, you are in fact accelerating. You did have some initial velocity, that is your v naught, your v at time 0. Very often that's going to be 0. In fact, I'll go over some examples with that. And then you have some final velocity, that is going to be your final v, which is there. That was an arrow if you didn't catch that. All right, so let's look at a relatively straightforward example of how to use one or two of these equations. So let's say that I have an example. In fact, give me a second, I'll write it out. All right, so here's an example. Bob goes from 0 to 60 in 3.5 seconds. So he's got a fast car. He's got some sort of hyper fast car. What is his average acceleration? And so I should say that these equations that I had given you before are for average values. So this acceleration represented by an A, I'm going to put a bar over it to meaning average. The velocity, bar over it meaning average. Sometimes you'll see a little bit of a little arrow sort of thing. It means that it's a vector quantity, something that we will look into a little bit more later. Displacement, by the way, is just usually represented as simply delta x, actually. All right, so let's go back down. First off, I need to express the units are terribly important here. We don't want to just go plugging numbers in right off the bat without blindly or while blindly looking at the numbers, which is a bit of an oxymoron. We have a number of 60 miles per hour, and this is the way most of you will write it. But I challenge you and I encourage you and kind of require you to write it like this: 60 miles per 1 hour. And the reason is we must convert this. You must recognize that the value must be in something that is recognizable in the physics world. We go off of kms, meaning that we go off of values of kilograms, meters, and seconds. So everything we do has to be in those root values. I know it seems a little bit weird that there's the kilo there, but in actuality it is true to say that kilogram is actually kind of the base unit. I know that seems counterintuitive, but it is. It is how all mass is actually defined, is by the kilogram, not technically the gram, as strange as that may be. So with that, we are going to have to convert this into meters and seconds rather than miles and hours. So let me move this down a little bit further, and we are going to do some conversions. Let me go through that with you. All right, so 60 miles per 1 hour, let's convert it. I'll put some parentheses around it so that way you recognize this as being a multiplication problem. If we have miles on the top, I'm going to multiply it by something which will have miles on the bottom. And so in 1 mile, I need to know how many meters there are, because that's what I want to get it to. So in 1 mile, there's 1,609 meters. That's not necessarily a number you have to have memorized, although it will save you some time to just go ahead and put that into your memory banks. And if from time to time you'll have to use the conversion, it is helpful to have it memorized. This is one that you do have to have memorized, that in 1 hour, and again, since the hours are on the bottom here, I need to put them on the top here in order to have them cancel. And in 1 hour, there is 3,600 seconds. Yes, you could go into minutes and then convert minutes to seconds, but frankly, let's just do this in one shot and simply memorize that 60 times 60 is 3,600. So 1 hour has 3,600 seconds in it. We have hours are canceled out, we have miles are canceled out, and now we just multiply everything through and come up with an answer. So we have essentially 60 times 1,609 times 1 divided by 1 times 3,600. Again, the units will be meters and seconds. In fact, let me just go ahead and finish that off. Let's see, 60 times the 1,609 and divided by 3,600 will give us, let me just erase this and put my number right in there, it will give us a 26.8, and again, our units are meters and seconds, so it's going to be meters per second. That's what we've converted this into. This final speed is going to be from 60 miles per hour to 26.8 meters per second. We are now expressing it in terms of meters per second. All right, so the whole process should look very familiar from chemistry. And in fact, if I can, let me make one last point of this here. That's not what I wanted. Let me finish this off by expressing what I'm really doing. If I were to multiply this by one other item, let's say I multiply it by 5 divided by 5. You should recognize that that's the same thing as multiplying it by 1. It doesn't change it at all. This is still true. So what am I doing in each of these cases? So if I look at this case right here, for example, I've multiplied it by 1,609 meters divided by 1 mile. Well, since 1,609 meters is equal to 1 mile, I've effectively multiplied it by 1. Those two things are equal to each other. Those things are equal to 1. I haven't changed what it fundamentally is, just kind of the way it's being expressed. So please keep that in mind when you are converting. It's still the same thing. 60 miles per hour is still the same thing as 26.8 meters per second. They're the same, just expressed differently. Let's get this moved out of the way and work on the rest of this problem. All right, whenever you work on a problem, we want to write down the things that are given. You want to write down the unknown items, or unknown item usually, and then you must put the equation that you start with. Put in parentheses, say starting equation. You have to write the starting equation. It's not just because I want you to either. On the AP test, that's what you must do, is you actually will get points for recognizing which equation to use and writing it down without any numbers into the equation starting off. That is the way it is expected that you are to be done. So with that, we're going to do it in this way. I know some of you really don't like it, but we're going to do it nonetheless. So what's given? Let's pull out the information from this problem. So the 26.8 meters per second, what is that? Well, that's a velocity, and in particular, it's a final velocity. I could put a little f in there for my own regard if I want, but it is simply a final velocity. Let's recall that. We have an initial velocity. Sometimes you'll see in textbooks it has a little I there for initial, by the way, but in most higher level textbooks you will see a subscript 0, and it's often said as v naught, and that is 0 meters per second. 0 miles per hour is the same thing as 0 meters per second. We have a time. In fact, we have a change in time that is equal to 3.5 seconds. And these are items that are given to us. We just need to express it. So please write it down, and please write it down vertically. I will show you why in a moment. We also need to know the acceleration. So the acceleration, I could put a little bar over that for average. And what is that? I like to put a little question mark here. And please write that down. And if you notice, by putting that vertically, we have all the things that we need. It is so much easier for us to recognize the equation that we need by doing it this way. One of the hardest things that people have is to recognize which equation to use. Writing down the variables, writing down the given and unknown with the variables here like this, help you recognize the equation that you need. And so here is the equation that I need. I can circle this one here. I have v minus v naught. I have v, and I have v naught. I have essentially delta here, now don't I? So I have got delta t, and I also need a, which is the entire other side of the equation. And so acceleration is equal to v minus v naught over delta t. Let's write it. We have to write the equation. Acceleration is equal to v minus v naught over delta t. And now we plug in our values. So we just pull the values from here on the left. So acceleration is equal to, we said 26.8 meters per second minus 0 meters per second. Yes, I realize that later on I'll not yell at you for putting in the 0. It's fine that you just leave that out. And that's going to be divided by the change in time, which is the 3.5 seconds. In fact, let me pull this over to the left a little bit more. And I'm going to then over here put in those numbers. Let's see. So if we take 26.8 divided by 3.5, that's going to give us a value of 7.66. And we need to look at our units. Our units are going to be in meters per second. In fact, as I said, we can actually get rid of that 0. It's not really relevant. Makes it easier for us to recognize our units. So I've got meters per second, which gives us our value of 7.66 meters per second squared. Or meters per second would be just as good. It's just as acceptable. So let me finish off by putting just a little bit of meaning to this. What does this whole function here mean? All right, well, let me rewrite it as that 7.66 meters per second per second. So 7.66 meters per second per 1 second. That's just another way of writing this acceleration. So what does that mean? It's like a double rainbow. You want to know what it all means. It means that this vehicle that Bob is driving is changing its speed or velocity. And for right now, let's just say that speed and velocity are the same thing. Okay, they are synonymous, at least for at this moment in time. I'll show you the differences later. Bob was changing his velocity by 7.66 meters per second for every second that went by. That means that after having driven for 1 second, after 1 second of time, he was going 7.66 meters per second. After 2 seconds, he's going 2 times that value. So he's 15 point something meters per second. After 3 seconds, he is 3 times that value. So for every second that goes by, he is moving that much faster. That is the meaning of acceleration. That is the meaning of these units of meters per second, or meters per second squared. That is the meaning behind it. So we will get more into those meanings behind the variables and the numbers later. Again, for right now, I just want you to recognize how to pick out the right variables from a word problem. Put those, get used to the process of writing down the given and the unknown, as I've got here on the left. Put your starting equation. That is a must. Put your starting equation without any numbers. You must break out of the habit of putting numbers down. Please get away from it, because there are going to be lots of problems where no numbers are given, and I mean none. And it is expected for you to manipulate the variables without numbers at all, and then actually extrapolate some sort of meaning to that new equation. That is something that you will have to do. Don't stress out about that too much, but please work on getting those habits developed where we try to resist putting numbers in so quickly. All right, so with that, I'm going to end. This is our straightforward topic on our average values for displacement, velocity, and acceleration. And we will work on putting those values, or taking those values from word problems and working those out. All right, so I will see you guys next time. Have a good one.